Now we will put all of our understanding together and learn how to graph a rational function. So the first thing that we do whenever we are attempting to graph any function is we determine the domain of the function. Then we can find and plot any of the intercepts of the graph. To find a y-intercept, we're going to let x equal 0. And to find an x-intercept, we're going to let y equal 0. One word of caution here is that whenever you find the x values, they have to be in the domain of the function. Then, we can use multiplicity to determine the behavior of the graph at the intercept, much like we did whenever we graphed polynomial functions. Then we can take any breaks in the domain and we can classify them as vertical asymptotes or holes. For any vertical asymptotes, we can use the multiplicity of the linear factor in the denominator to determine the behavior on either side of the vertical asymptote. Then we can find any horizontal or oblique asymptotes. Once we find any horizontal or oblique asymptotes, we can find any points of intersection between the graph and the asymptote. Then we will plot any additional points. Those points will be determined by choosing x values between or beyond x-intercepts and discontinuities. Then we will put all that together and graph our function. So let's take a look at an example. So let's start off by finding the domain of the function. So we can set the denominator equal to 0, and that's going to yield x equals 2, and so the domain will be negative infinity to 2 union 2 to infinity. Now let's find any intercepts. To find the intercepts, let's start with the y-intercept, if there is any, which we can let x equal 0. So r of 0, we're going to substitute 0 in for x, will give us negative 12 over negative 2, which is equal to positive 6. So we can plot that on our graph. Now, any x-intercepts. For this, we're going to let y equal 0. So we have 4x minus 12 over x minus 2. Set that equal to 0. Multiply both sides by the denominator and clear our fractions. We get 4x minus 12 equals 0, or simply x equals 3. X equals 3, we check to make sure is in the domain of our function, and it is. So that is our x-intercept. And you'll notice that the multiplicity of that is 1, so we're going to cross there. Now let's look for any vertical asymptotes or holes. So, to do that, let's see if we can simplify r of x. We can factor out a 4 from the numerator, and then the denominator is x minus 2. It cannot be factored. Notice nothing cancels. So that means that the denominator, which is still there, corresponds to a vertical asymptote of x equals 2. So x equals 2 can go on our coordinate plane as a vertical asymptote. Now, do we have any horizontal asymptotes or oblique asymptotes? Notice the degree of the numerator is 1. The degree of the denominator is 1. So since those degrees are the same, then that means that we have a horizontal asymptote, and we look at the leading coefficients. So 4 over 1. The leading coefficient there in front of the x is 1. So 4 over 1. So we have a horizontal asymptote. Y equals 4. Now, whenever you write horizontal asymptotes or vertical asymptotes, be sure that you write them as equations. Y equals for horizontal asymptotes. Vertical asymptotes are x equals. So let's go ahead and graph that horizontal asymptote. Y equals 4. Let's label these. Y equals 4. This was x equals 2. And now let's go ahead and see if there are any points of intersection between our graph and the horizontal asymptote. So we're going to set r of x equal to the corresponding value from our horizontal asymptote. So 4. So r of x was 4x minus 12 over x minus 2. That's equal to 4. Let's multiply both sides by x minus 2. So the left-hand side is just 4x minus 12. The right-hand side is 4x minus 8. Now if we subtract 4x from both sides, we get negative 12 equals negative 8, which is always false. So therefore there is no solution, and therefore there is no point of intersection. Now let's go ahead and take a look at what we have. What we can do now is choose some values between and beyond our x-intercepts and vertical asymptotes. And if we had any discontinuities like holes, then we would also include those. So the only discontinuity that we have is a vertical asymptote. So let's look at our x-axis. We need a value to the left of 2, between 2 and 3, and then to the right of 3. So to the left of 2, we already have one. We found the y-intercept, 0, 6. So no need to do extra work there. Between 2 and 3, we can choose 2.5. And then to the right of 3, we can choose a value like 4. So if we substitute 2.5 in, what do we get for r of x? And then what do we get for y if x is 4? Go ahead and plug those in and see what happens. So if x is 2.5, we get negative 4. If we put in 4, we get 2. So let's plot those. 2.5, negative 4. Let me change the color on that. And then 4, 2. So now, as we look at each one of these points, we know what happens. Because if we look at 0, 6, I know that to the left of that I need to approach my horizontal asymptote, and then to the right of that I need to approach my vertical asymptote. Now, if we look at this point, I know I'm going to have to approach my vertical asymptote, and then I'm going to have to approach the x-intercept. Now remember that we're crossing our x-intercept because of the multiplicity, and then as I pass through this point, I'm going to have to approach my horizontal asymptote. Now if you remember, our vertical asymptote was from x minus 2. X minus 2 had an exponent of 1, so therefore to the left and to the right of my vertical asymptote, I'm going to have opposite behavior because it's an odd multiplicity. So let's take a look at another example. So here we have a rational function. We'll start off by finding the domain. So we'll set the denominator equal to 0. So 2x squared minus 18 equals 0. Now this we could use the square root principle to solve, or we can factor out the 2 and then use a difference of squares. If we use the square root principle, we would move the 18 over, divide by 2, take the square root. Or if you wanted to factor it out, you would go through this process. So now we would have 3 factors, and the question is, can they be 0? 2 can't be 0, but x plus 3 could be 0 if x equals negative 3, and if x is 3, we could have 0 for that factor. So we get the same 2 solutions. So our domain is negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. Now let's find any intercepts. So to find any x-intercepts, we let y equal 0. So we would have x squared over 2x squared minus 18 equals 0. Now, if we multiply both sides by 2x squared minus 18, the left-hand side, we would get x cubed. And then on the right-hand side, we get 0. So, take the cube root of both sides, we get x equals 0. And 0 is in the domain, so therefore x equals 0 is our x-intercept. Now for your y-intercept, it's less eventful. We let x equal 0, and we get r of 0, which is going to be 0. So your y-intercept is y equals 0. Now whenever it comes to finding vertical asymptotes in holes, if we look back at our original function, we've already factored the denominator, but notice there's no common factor, and so therefore nothing's going to cancel. So both of our breaks in our domain consist of vertical asymptotes. Now we can find any horizontal or slant asymptotes. Now if you notice, the degree of the numerator is 3. The degree of the denominator is 2. So 3 is 1 more than 2, so this is going to have a slant asymptote. So to find the slant asymptote, we will use division. We cannot use synthetic division here, so we're going to have to use long division. So we will take x cubed and divide it by 2x squared minus 18. Now this is a little weird, so probably the best thing would be to go x cubed plus 0x squared plus 0x plus 0 to fill in our missing terms. So 2x squared is going to need what in order to become x cubed? Well, 2 needs to be multiplied by what in order to get 1? The answer there is 1/2. Now, what does x squared need to be multiplied by to get x cubed? It needs an x. So now we take 1/2 x and we multiply by our divisor. Now, it's important that we're careful in lining up our terms, x cubed, x squared, and x. So 1/2 x multiplied by 2x squared is our x cubed. But whenever we multiply 1/2 x by negative 18, we are going to get negative 9x. So we should put that in the x column, negative 9x. So now we subtract. So we have x cubed minus x cubed, and that's going to go away. 0x squared minus 0 is 0x squared. 0x minus negative 9x is positive 9x. We can bring down the 0, but you'll notice that 2x squared, we're not going to make into 9x. So our slant asymptote is going to be y equals our quotient. 9x is our remainder. So our slant asymptote, or oblique asymptote, is y equals 1/2 x. So let's go ahead and graph that. So let's go ahead. We also have to graph our vertical asymptotes. X equals -3. I don't think I wrote that down, that those corresponded to our vertical asymptotes. So let me go ahead and write that down. Vertical asymptotes, x equals 3, and x equals -3. And again, the reason why x equals 3 and x equals -3 are vertical asymptotes is because they're factors that remain in our denominator even after factoring. So, going back to our graph, x equals 3 and -3 are our vertical asymptotes. And we said that y equals 1/2 x is our slant asymptote or our oblique asymptote. So that is a line with a slope of 1/2 and y-intercept of 0. So we're going to start with our y-intercept. We're going to go up 1 to the right 2. And we can go up 1 to the right 2 over and over and over again. Or we could go down 1 to the left 2. Now we need to determine, are there any points where our graph intersects our oblique asymptote. So to determine that, we take our function, which was x cubed over 2x squared minus 18. And we're going to set that to our oblique asymptote, 1/2 x. To solve this, we will multiply both sides by our common denominator. So we have 2x squared minus 18, and we have 2. That's easy enough. There are maybe other ways to have done this, but this is probably going to be the easiest to see. X cubed over 2x squared minus 18 times 2 times 2x squared minus 18 equals 1/2 x times 2 times 2x squared minus 18. So now 2x squared minus 18 and 2x squared minus 18 cancel, and we're left with 2x cubed. 1/2 and 2 cancel, and we are left with 2x cubed minus 18x. If we subtract 2x cubed from both sides, we get 0, and we're left with 0 equals -18x. Divide both sides by -18, we get 0 equals x. So we intersect at 0, which is clear because we've already said that 0, 0 is on our graph, and our asymptote flows through that. Then we label that slant asymptote, or that oblique asymptote, as y equals 1/2 x. So now we are ready to plot some additional points. So we have x and r of x. So we need to choose x values that are between or beyond vertical asymptotes. We don't have any holes, and then any x-intercepts. So vertical asymptote is at -3. We need a value to the left of -3. So let's choose -4. Then we need a value between -3 and 0. We can choose -1. Then between 0 and 3, we can again choose 1, or not again, but we can likewise choose 1. And then to the right of 3, we can choose 4. So let's plug these in and determine what our y values are. So if we substitute -4 in, we get, as a decimal, it's going to be easier to graph, about negative 4.6. If you substitute negative 1 in, we get positive 1/16, which is 0.0625, which we can only really get an idea of one decimal place, so I'm going to approximate that to 0.1. If you substitute 1 in, you get negative 1/16, so we're going to just approximate that as negative 0.1. And then likewise, 4 is going to give us positive 4.6 approximately. So let's plot these points on our graph. Negative 4, negative 4.6, negative 1, about 0.1, and then 1, about negative 0.1, and then 4 is going to be at 4.6. So now we know that our graph, as it passes through this point to our left, is going to have to obey the slant asymptote or oblique asymptote. And then as we approach our vertical asymptote to the right, and then as we trend toward our vertical asymptote and pass through our points. Now, our multiplicity of our x-intercept shows us that it's going to cross because it's an odd multiplicity. And then, again, on the right, we have something similar as to what we had on the far left. And so here's our graph. So let's begin this example by again looking at the domain of our function. So we set the denominator, x squared plus 2x minus 3 equal to 0. Let's factor that. We have x plus 3, x minus 1. And so that yields x equals negative 3, positive 1. So we exclude those values. So the domain is negative infinity to negative 3, union negative 3 to 1, union 1 to infinity. Now let's find any intercepts. So to find the intercepts, let's start off with the x-intercept and let y equal 0. So we have x minus 1 over x squared plus 2x minus 3 equals 0. If we multiply both sides by our denominator, we get x minus 1 equals 0. And that yields x equals 1. But wait, x equals 1 cannot be an x-intercept because 1 is not in our domain. So that tells us there are no x-intercepts. Now let's look at our y-intercept, if there is one. To do that, we let x be 0. So we get 0 minus 1 over 0 squared plus 2x minus 3 will just be minus 3. So we get negative 1 over negative 3. That's a positive 1/3. So our y-intercept is y equals 1/3. So let's put that on our graph. Now let's look for any vertical asymptotes and any holes. So to do that, we take r of x and we factor, which we've already done, the denominator. The numerator cannot be factored. So we obtain 1 over x plus 3 because we can cancel the x minus 1s. Now x minus 1 only cancels as long as it's not 0. So we can only cancel it as long as x doesn't equal 1. So this means that we have a vertical asymptote of x equals negative 3 because that's the factor that remains in our denominator. Then we have a hole also. That corresponds to the 1 that we see here. Now, 1 comma 1. We take and we plug 1 into that simplified fraction. 1 over 1 plus 3 is 1/4. This is where our function would be, but we are going to delete that. We're going to make a hole in our graph. Now, do we have any horizontal asymptotes or oblique asymptotes? Well, what is the degree of the numerator and the degree of the denominator? The degree of the numerator is 1. The degree of the denominator is 2. So, the denominator has a higher degree, so we have a horizontal asymptote, y equals 0. So let's go ahead and put some of this information on our graph. We've already put in our y-intercept. Vertical asymptote is x equals -3. We had a hole at 1 comma 1/4. And then we have a horizontal asymptote at y equals 0. Now, does our graph ever intersect the horizontal asymptote? Well, for it to cross our horizontal asymptote, it would need to cross our x-axis. But we've already said there are no x-intercepts, so no reason to check that. So let's go ahead and plot additional values. So between and beyond any vertical asymptotes or discontinuities. So we need a value to the left of -3. We can choose -4. And then we need a value between -3 and our discontinuity of 1. But we already have 1. So no need to double any work. We already can use our y-intercept. And now any value to the right of 1 would be sufficient. So let's try 2. So if we put in -4 and 2, what do we obtain? If we put in -4, we should get -1. And if we put in 2, we get +1/5, which is 0.2. That's even closer to the x-axis than the others that we have graphed there. So it might not be easily distinguished. So I'll zoom in. So -4, we obtained -1. And for 2, we obtained 1/5. So now we approach our horizontal asymptote, and then we're going to approach our vertical asymptote, and then we're going to approach our vertical asymptote from this side, go through our point, meet up at our hole, and then approach our horizontal asymptote. And there's our graph.